Hello my dear students. Today we are going to discuss about the topic electrochemistry. Conductivity cells. There are various types of specially prepared cells that are used in the conductance measurements, and these cells are called conductivity cell. Here it is shown a schematic representation of simple type of conductivity cell in this slide. These conductivity cells are made up of Pyrex glass and is fitted with two platinum electrodes. These platinum electrodes are coated with platinum black. So you can see the platinum electrodes, two platinum electrodes, and these platinum electrodes are coated with platinum black. These platinum electrodes are welded to the platinum wires and they are fused into the bottom of two thin glass tubes containing some mercury for making contact to the circuit by means of copper wire. The glass tubes are usually fixed rigidly into the ebonite cover so that the distance between the electrodes remains constant. So you can see the Pyrex glass tube for the conductivity cell, then the platinum electrode which is coated with platinum black and that is fused to the glass tube through the platinum wire, and the glass tube contain mercury. For the electrical contact, there are two copper wires. Now these small glass tubes, narrow glass tubes are fixed by the ebonite cover, rigidly fixed by the ebonite cover, so that the distance between these two small glass tubes remains constant. Next is cell constant. Cell constant is the ratio of distance between two electrodes in a conductivity cell to the area of cross-section of the electrode. That is, it is denoted as G star. So the specific conductance, we know the specific conductance of an electrolyte is given as K equal to G into L by A. That is, specific conductance is equal to conductance into cell constant. So the cell constant is a factor with which the observed conductance of an electrolyte solution is to be multiplied in order to get its specific conductance. Now, if L is the distance between the two electrodes and A is the area of cross-section of these electrodes, the G star, that is the cell constant, is given as G star equal to L by A. We know that L and A are constants, therefore the quantity L by A is also a constant. So this cell constant is the factor with which the observed conductance of an electrolyte solution is to be multiplied in order to get its specific conductance, that is K equal to G into G star. Next is variation of specific conductance with dilution. Actually, the specific conductance of an electrolyte solution decreases with dilution. So we know what is specific conductance. What is specific conductance? Specific conductance of an electrolyte solution is the conductance of unit volume of the solution kept between two platinum electrodes with unit area of cross-section and kept unit distance apart. So on dilution, that is on decrease in the concentration, the volume of the solution increases. And consequently, there occurs a decrease in the effective number of ions per unit volume of the solution, so that the conductance per unit volume decreases. So in other words, the conductivity, that is the specific conductance, decreases. So the specific conductance decreases with dilution. Now next we will see the variation of molar conductance with dilution. The molar conductance increases with increase in dilution. So the molar conductance of an electrolyte solution increases with increase in dilution. Okay, so molar conductance is given as lambda m. Molar conductance is equal to K into V dash. That is, V is the volume of the solution containing 1 mole of the electrolyte. And if M is the molarity of the solution, lambda m is also given as lambda m equal to K into 1000 by M. And it is also can be found out from the equation K by C, where C is the concentration. So it has been found that the decrease in K on dilution of the solution is more than compensated by the increase in its volume or decrease in its molarity, so that the lambda m increases with dilution. So here we can discuss this variation of molar conductance with dilution with the help of a graph. So this is a plot of lambda m versus root C for strong electrolyte and weak electrolyte. The increase in lambda m with dilution is seen for both strong and weak electrolytes, but the manner in which it occurs is found to be different for these two types of electrolytes. This difference in behavior is reflected in this plot given here. So we can see here the rate of increase in lambda m with increase in dilution is rather slow for strong electrolyte, but it is much more rapid for weak electrolyte. We can see here, this is the plot of strong electrolyte and this is the plot of weak electrolyte. So particularly at a higher concentration, this variation is rapid for weak electrolyte. So here this is this axis shows the concentration. So for lower concentration, that is for on dilution, at higher dilution, the increase in lambda m is rather rapid for weak electrolytes. So for strong electrolyte, the molar conductivity reaches to a limiting value at very low concentration, and it is known as the molar conductance at infinite dilution or limiting molar conductivity, and is denoted as lambda m0. Also it can be written as lambda m infinity. So for strong electrolyte, the increase of lambda m with dilution can be represented by the equation lambda m equal to lambda m0 minus A into root C, where A is a constant at constant temperature for a particular type of electrolyte because it depends upon the charges of the constituent cations and anions of the electrolyte. That is, for example, for 1,1 electrolyte NaCl, KCl, etc. That is here each ion carries unit charges, so Na plus and Cl minus, for example. So for that type of electrolyte, A is a constant. For 2,1 electrolyte, for example CaCl2, calcium chloride, in that we have the ions Ca2 plus and Cl minus. For that particular type of electrolyte, the A is a constant, like that. So the experimental curves lambda m versus root C for strong electrolyte is found to be more or less linear in accordance with the above equation. So with the intercept lambda m0 and slope minus A. And the case of weak electrolyte, it fails to give a limiting value of lambda m in a measurable range of concentration. Now the factors which influence the variation of molar conductance with dilution are the number of ions, interionic attraction and the ionic mobility. So the number of ions, interionic attraction and ionic mobility. So on increasing dilution, there is an increase in the number of ions in the case of weak electrolyte. and a decrease in interionic attractions for both strong and weak electrolyte, and an increase in ionic mobility for both strong and weak electrolyte. So we can see one by one. So first we will see the case of strong electrolyte. For strong electrolyte, the molar conductivity is high even at low dilutions, since the ionization of electrolyte is complete. So with increasing dilution, the molar conductivity increases slowly or more or less steadily. This is because with dilution, the interionic attraction decreases, thereby the velocity or the ionic mobility and the conducting capability of the ions increases. So as the ionic mobility increases, that will increase the conducting capability of ions. So at high dilution, the interionic attraction becomes negligible and the molar conductivity reaches its maximum limiting value, which is known as the limiting molar conductivity or the molar conductivity at infinite dilution. Now next, the case of weak electrolyte. The molar conductivity is low at low concentration, since the electrolyte is only slightly ionized. With increasing dilution, the molar conductivity increases gradually as the number of ions increases due to the greater ionization of the electrolyte. So, as dilution increases, the interionic attraction decreases, and this causes an increase in the velocity as well as the conducting capability of the ions, and this contributes to an increase in molar conductivity. So on higher dilutions, the effect due to the greater ionization and reduced interionic attraction becomes so pronounced that the molar conductivity increases rapidly. Next is degree of dissociation. Degree of dissociation. Degree of dissociation of an electrolyte in a solution at a given concentration is defined as the fraction of the total number of moles of the electrolyte that has dissociated in solution into ions. So we can assume that the infinite dilution, when the limiting value of the molar conductivity lambda m0 is reached, even a weak electrolyte is completely dissociated, that is, its degree of dissociation is unity at infinite dilution. So suppose lambda mc represents the molar conductivity of the electrolyte solution at a specific concentration C. Then assuming lambda m is independent, that is independent on the number of ions produced, the degree of dissociation alpha at a particular concentration C is given as alpha equal to lambda mc by lambda m0. Now the factors affecting this degree of dissociation are nature of electrolyte, nature of solvent, concentration, temperature and presence of ion. So that's all for today's lecture. Thank you.